It's a lecture over introducing basic stoichiometric conversions, going from mole to mole, going from mole to gram and gram to mole, and then going from gram to gram. And so, quote we have here: one for you, one for me, two for you, one, two for me, three for you, one, two, three for me, by Bugs Bunny. What we're trying to accomplish in this are learning goals that we have. Students will understand the role of the mole ratio. It's a huge concept in stoichiometry. It's what we've been building up to, the mole ratio in stoichiometric calculations. Number two, students will be able to convert from moles of a reactant or product to another reactant or product. So we're going from moles of anything that we have into moles of any reactant or any product. And lastly, students will be able to integrate their previous knowledge of dimensional analysis to include stoichiometry for any reactant and product. So what we're trying to do here is we're trying to include anything that we could possibly have: grams, moles, all of that. So what we already know about dimensional analysis. Now, dimensional analysis is the useful tool for converting between two equivalent values. We have the statement of equality. When we're looking at this, we're trying to convert from 26.2 miles into meters, and so we need conversion factors. We have right here, we have our 1 mile equals 1.6 kilometers, and we have 1 kilometer equals 1,000 meters. Now, both numbers in the vertical column are equal. 1 kilometer equals 1,000 meters, and 1.6 kilometers equals 1 mile. So these equal each other right here. And we set them up so that we can see that their units cancel out. So we have our miles right here, 1 mile, and then we have our kilometers up there. And we see that those guys will cancel, and we get here, we have kilometers right there, kilometers right there. Okay, and we see that miles cancel, kilometers cancel, and we're left with our unit that we want, which is meters. And so we go 26.2 times 1.6 times 1,000 will give us something right around 41,920 for an answer. So that's dimensional analysis. Now, what we already know about chemical equations. Okay, we talked about this a lot in the last unit. It's the law of conservation of mass. So the law of conservation of mass states that you must have an equal number of each atoms before and after the reaction, but they can be arranged differently. So we have to have the same number of atoms, but we can rearrange them. In that chemical reaction, that's what it does. It rearranges everything so we can get something a little different. Okay, now what we learned in the lab, we looked at a titration for this, and we're looking at that titration setup. We used this to figure out what kind of copper or what kind of iron we actually had. The titration is very useful for that quantitative, okay, all those numbers, or that qualitative, we're looking and describing it, analysis. This is very useful in getting the ratio. The ratio can be useful for identifying and predicting reactions. So titration is a very good thing that we use to help us predict what the products are, figure out what those oxidation numbers were, what type of reaction we actually had. So what does the chemical equation give you? Now, when we're looking at it, we look at our chemical equation, and this is a combustion reaction. We have our methane here reacting with our oxygen to produce our CO2 and our water. Well, the chemical equation shows us the mole ratio, and all the mole ratio are these guys up front, okay, our coefficients. Now, our coefficients, see a 2's right there, a 2's right there. If it doesn't have a coefficient, it's understood to be 1, okay? So when we're looking at this, carbon dioxide has a coefficient of 1, methane has a coefficient of 1. So there's our coefficients, the 1, the 2, the 1, the 2. That gives us our mole ratio. That's the ratio in between them. So 1 mole of methane equals 2 moles of water. 1 mole of methane equals 2 moles of oxygen. There's a 2. 1 mole of methane equals 2 moles of, we have water again, but basically whatever it's set up to, that's what it equals. Okay, so we can also say that the 2 moles of water equals 1 mole of CO2. We can say that our 1 mole of CO2 equals 2 moles of our oxygen. And so everything, all the coefficients, they give us that mole ratio. They set everything up for us. Okay, so using the mole ratio, what it does is it allows you to predict the amount, so the quantitative amount of each product. How many moles of water will be produced when 25 moles of methane is combusted? So when we're looking at this, we have 25 moles of methane, okay, and it wants to know how many moles of water. Well, what's the ratio? We're starting with 25. Okay, we always start with the number that the problem gives us. Well, what's our mole ratio between? We have our methane, so we're starting with at 25 moles, and we're going to water. What's the ratio? Well, it's a 1 to 2 ratio. So 1 mole of methane equals 2 moles of water. Okay, so it's that dimensional analysis set up for us again. We see that they equal each other, and so we just go 25 times 2 is 50, divided by 1 is just 50. So we know that 25 moles of methane will produce 50 moles of water. Okay, let's look at an example here. It says balance the equation below and determine the appropriate mole ratio of moles of octane to moles of calcium carbonate. So we're going to have to balance all of these out. The main thing with stoichiometry is it only works with a balanced chemical equation, so we have to start there. So in our first equation, what we have, okay, let's start with our nonmetal, which is carbon. We have 8 here, so we need 8 over there, so we put an 8. Now we have 8 carbons. We have 16 plus 1, 17 oxygens, so that's not going to work for us. So we got to balance out our oxygens. So 17, there's nothing we can multiply, or a whole number we can multiply that to. 2 times whatever won't give us 17, so therefore we have to work it out. Let's look at our hydrogens. Hydrogens, we have 18 right here. We only have 2 over there, so we could put a 9 here. Let's see if that helps us out with the oxygens. So now we have our hydrogens are nice and balanced out. Our carbons are nice and balanced out. Our oxygen, we have 16 plus 9. So 16 plus 9 is going to give us 25. Still doesn't help us. So let's go ahead and come back and put a 2 right here. Anytime in a combustion reaction doesn't work out for us nice and neat the first time, well, we just come back and put a 2 in front of that hydrocarbon. So now we have our 16 carbons, which now we need 16, so we go over here and we put our 16 right there. Now we have our 16 carbons, oxygens, we have our 32 plus that's 33. Okay, now we have to look, we have our hydrogens, we have 2 times 18 is going to give us 36, which we'll need to go ahead and put an 18 over here, because 18 times 2 is 36. Now let's look at our oxygens. We have our 32 plus our 18, and that would be 50, which we can do that. We put a 25 here. That one was a hard one to balance. Next one, we see start with our carbons. We have 1 carbon right here, 1 carbon right there. That's okay, it's good. Look at our oxygens. We have 2 right here plus 1, so it's 3. We have 3. Hydrogens 2 and 2. So that helped us out. That was nice and balanced. So it's just 1s all the way across. Okay, and then lastly, the last one that we have, we see that we have our 2 carbons. We have 2 carbons right there because that 2 distributes out. We have our 3 plus 3 is 6, which we have 6 oxygens right there. We have our 1 calcium, and we see we have 2 hydrogens, so that's balanced. So really, we only had to balance the first one. Everything else is going to be 1s straight across. So we're looking at what's the mole ratio between octane and our calcium carbonate. So in this series of reactions, what we see is that we have our ratio. We just pick out what we have. Well, here is our octane, which is 2 moles, and look at calcium carbonate, which we have right here, or calcium bicarbonate, which is right there, and we see that it's a 2-to-1 ratio. Okay, so let's look at this A2, example A2. It says write the correct mole ratio for moles of TNT to moles of nitrogen gas. So TNT is right here, and then nitrogen gas is right here, and that gives us we just looked at the coefficients, a 4 to 6 ratio. So 4 moles of TNT equals 6 moles of N2. Alright, next example, we see that we have example A3. It says 35 moles of, we see our potassium permanganate are present in a sample that is mixed with hydrochloric acid according to the equation below. So we have this is potassium permanganate, and we have 35 moles of it. And it wants to know how many moles of each product would you expect. So in working this out, we always start with the number that it gives us in the problem. So we have our 35 moles of potassium permanganate. So 35 moles of our KMNO4. Okay, so what we're going to do is we're going to start every single problem with that. So we set it up. There's our potassium permanganate, and set up our stoichiometric relationship, do our dimensional analysis. So any mole, of our product, we have 1, 2, 3, 4 products. So we'll have to do this 4 times, but we just use 4 different mole ratios. So to our first product, potassium chloride, it's a 2-to-2 mole ratio. So what that means is we have 2 moles of KMNO4 equals our 2 moles of KCl. And then all you do is match everything up. Okay, that's going to go on the bottom. 2 moles of our potassium permanganate, because that cancels out. And then you just put the other part of the mole ratio on top. And so what you'll see is a 2-to-2 ratio is just like a 1-to-1 ratio. So we multiply by 2 and then divide by 2. So our first one will get our 35 moles. Okay, and what we can see is in the next one, it's the same ratio. So it's a 2-to-2. So the only thing that will change is on the top, we'll have our, it's still a 2-to-2 ratio, but we'll have it, instead of moles of our potassium chloride, it's manganese chloride, in particular manganese 2 chloride. So it's MnCl2, but it comes out to be the same thing, okay, MnO4, because it's the same ratio. So this is 35 moles. Okay, the next one is a 2-to-8 ratio. So 2 moles of KMNO4 equals 8 moles of H2O. Okay, so when we're setting it up, do the same thing, start with the same exact number. Okay, and then all we would do is, for dimensional analysis purposes, we put that on the bottom because that cancels that unit, and then put the other part on top. So all you would have here is you would go 35 times 8, and then you go 35 times 8 and all divided by 2, and that will give us right around 140 moles of water. And then our last one we see is a 2-to-5 ratio. Okay, so the bottom stays the same because it's 2 moles of this, 5 moles of HCl. So we just put 5 moles, not HCl, but Cl2 on top. So 35 times 5, all divided by 2, and that'll give us 87.5, and that's moles of chlorine. Alright, so now we know how to use the mole ratio. So we're going to look at how that mole ratio plays into other parts of our stoichiometry. Main thing when we're working here, we've seen this part before when we worked with just the mole and grams and atoms or number. We saw that before. The only thing that we've really added is we've added in the mole ratio. Okay, so the way that this works, remember, when you start with mole, you always multiply. If you start with anything else, you're going to divide. So when looking at this, if we start with grams, so say we start right here, and we go from grams to moles, well, we're going to divide by our gram formula mass. Now, the thing that we have here, the addition, what's new is the mole ratio. What the mole ratio allows us to do is to convert between different substances in a chemical equation. So, if I want to go from grams of anything to back to moles of whatever's in the equation, what I can do is go from grams to moles, use the mole ratio, and I can figure out how many moles I have. Now I can go back, so say I wanted to get grams. So I started with grams of a substance, and I wanted to figure out, we'll say this is grams of A, and I wanted to figure out how to convert to grams of B. So A is anything. Okay, it's in the chemical equation. It's the first thing that you start with. It's the number that it gives you. So I can go from grams to moles of A by dividing by my gram formula mass. And then I can use my mole ratio to change to anything else in the equation. So I can go to moles of B, whatever B is. It doesn't matter what it is. And then if I want to go back, so if I'm in moles and I want to go back to grams of B, I just use that gram formula mass and multiply, and I could get grams of B. Okay, basically what this boils down to, anytime you see grams, whatever you see it by, if you see grams, whatever you see it by, or mass or anything like that, you're going to need the gram formula mass. Okay, and then once you get it to moles, you can convert it to anything else in the equation by using the mole ratio. And then again, if I want to get it back in grams, I want to figure out how many grams I have, well, I need the gram formula mass. So anytime I go from grams of something to moles of something, I need the gram formula mass, or if I'm going from moles to grams. Anytime you see grams, whatever it's by, you need that gram formula mass. And then we can always use Avogadro's number to figure out how many atoms or how many molecules that we have. So looking at dimensional analysis again, we're looking at it. Here we have our nitroglycerin, and we're saying that we have 5,000 grams of it. Well, if I want to convert it to something else, I have to use the mole ratio. So it has to be in moles. So I have my 5,000 grams. Remember, if you ever see grams, you need the gram formula mass. Well, the gram formula mass of nitroglycerin is about 227 grams per mole. So that's where we see this relationship. 1 mole equals 227 grams. That's my molar mass. And then here, if I'm converting it into CO2, well, look at my ratio. My ratio is a 1 to 3. So what I see is I have a 1 mole of nitroglycerin for every 3 moles of CO2. My units cancel, and I'm left with a unit of moles of CO2. So all we have to have is, if we start with grams, we need the gram formula mass. And then the mole ratio lets me transition from anything to something else in the equation. So let's look at an example. It says that 50 grams of iron reacts with excess oxygen to form iron 3 oxide. How many moles of iron 3 oxide are produced? So what I'm looking for is moles of iron 3 oxide. What am I starting with? I'm starting with 50 grams of iron. Well, the first thing we need in any stoichiometric conversion is we have to have a balanced chemical equation. Okay, so what do we have? Well, we have our iron reacts with excess oxygen. So iron is Fe. E. Anytime we write an element, we check, is it a diatomic? Iron is not. Okay, it's reacting with excess oxygen, which is O, which in this case is oxygen a diatomic? Yes, it is. So we put O2. Okay, and it forms iron 3 oxide. So iron, which has a +3 oxidation number, and oxygen, which is -2. So we go ahead, crisscross this. I'm crisscrossing because this is an ionic compound, and we get Fe2O3. So there's my chemical equation. Is it balanced? No, not really. So first, let's start with our metals. How do we balance that out? Well, we can take this. Let's move it kind of in the middle. There we go. Oh, missing that little part of iron. Start with our metals. Yes, we can balance that out really simple and put a 2 right there. But then our oxygens aren't balanced. Okay, and so what we're going to have to come back and do is oxygen we see is a 2 and then there's a 3. Anytime you see a 2 and a 3, normally the common value is going to be a 6. So how do we make 6 oxygens on this side? Well, it's 3, and then we put a 2 right here. Okay, remember that 2 distributes to iron as well. So my oxygen are balanced, but now my irons are 4, so we just put a 4 right there. Okay, so going on with the problem now. Now that we have a balanced chemical equation, we can actually work out the problem. Now remember, I told you, anytime that you see grams, you need the molar mass. Whatever it says grams by. So it said 50 grams of iron. So guess what you're going to need? You're going to need the molar mass of iron, which is right around 56. We'll round it to there. So 1 mole of iron equals 56 grams of iron. Okay. Now, the other thing we need with excess oxygen to form that, how many moles of iron 3 oxide? So we need moles of iron 3 oxide. So anytime we're dealing with stoichiometry, we're going to use the mole ratio. So we're going from grams of iron to moles of iron 3 oxide. So what's our mole ratio? Well, it's a 4 to 2. So 4 moles of iron equals 2 moles of Fe2O3. Okay, those are our conversion factors. We call these over here our statements of equality, and then we just set up our problem. So 50 grams of iron, set it up. Since this says grams of iron, I use my molar mass, 56 grams of iron. Put the other part on top, equals 1 mole of iron. Okay, keep going. And we see that now these units cancel, grams cancel. Now we're in moles, and I'm transitioning and converting from iron to iron 3 oxide, so I need my mole ratio. So for, undo that. So 4 moles of iron would go on the bottom, and our 2 moles of iron 3 oxide would go on top. Cancels it out, and then all I do from here is just multiply out the top. So 50 times 1 times 2, all divided by 56 times 4, which if I multiply it out correctly, I should get something right around 0.446, and that would be moles of our iron 3 oxide. Okay, on our next example, it says an unknown quantity of ammonium phosphate, okay, is reacted with excess barium nitrate to produce 500 grams of ammonium nitrate. How many moles of ammonium phosphate were in the original sample? So when I'm working this one out, I first got to start with my balanced chemical equation. So the first thing I have, my first reactant, is ammonium phosphate, which ammonia is NH4 with a positive charge, and phosphate is PO4 with a -3 charge. We crisscross and we get our NH4 3 and our PO4, which we take that guy, and that's our first reactant that we have. Okay, and that's reacting with our barium nitrate, which barium is Ba, and barium has a +2 oxidation number, so it'll be 2 plus, and then is bonded to nitrate, which is NO3, negative charge, crisscross, and we get our BaNO3 2. Okay, so those two guys are reacting together. Okay, and they go ahead and they produce out our two products. It's a double replacement reaction. So our two products are going to be, the first one is ammonium nitrate. So NH4 positive charge, NO3 negative charge crisscross, and we get NH4NO3. Okay, plus our other one is going to be our barium will now be bonded to our phosphate. So barium is Ba 2 plus, phosphate PO4 3 minus, crisscross, and we get Ba3 PO4 2. Okay, there's our chemical equation. Now all we have to do is balance that guy out. So when we balance this out, looking at it, let's start with our metals first. So we have our barium, which, do these a different color. Barium, we have 1 here, 3 there. So to make that, we put a 3. Okay, now we have to balance out our ions. We see that phosphate is 2 right here, but we see that nitrate, that's going to be 2 times 3 is 6. So we can balance that out first. Either one, it really doesn't matter. We'll put a 6 right here to balance out the nitrates, and our ammonia needs to be 6, and our phosphate needs to be 2, so we'll put a 2 right there. So we get our nice, neat, balanced equation, which will give us our mole ratios, which we'll need a lot later. So let's look at what we're starting with. In the problem, we're starting with 500 grams of ammonium nitrate. So we have our 500 grams of our ammonium nitrate, which that's NH4NO3. That's what we're starting with. Okay, so let's look at the rest of the problem. So we know we're starting with that, and we want to figure out how many moles of ammonium phosphate were originally in the sample. So here is our ammonium phosphate. So we have 500 grams of ammonium nitrate. Anytime we see grams, what do we need? We need the molar mass. So we're going to write that one down first, and we get our molar mass of our ammonium nitrate is right around 1 mole of ammonium nitrate, which is NH4NO3, is right around 80 grams. Oh, not 8 grams, but 80 grams of NH4NO3. Okay, the other thing that we always need our mole ratio. So what's our mole ratio between these two guys? It is a 2 to 6. So 2 moles of our ammonia phosphate equals 6 moles of our NH4NO3. Okay, so now that we have everything set up, we can set it up in our stoichiometric relationship or dimensional analysis over here. So 80 grams goes on the bottom. That equals 1 mole, which goes on the top. Continue it on out because we want, now that we have it in moles, we can now convert into our moles of ammonium phosphate. So we go ahead and we see that moles of that 6 go on the bottom because that's what we originally have. That goes up on the top, and we see that we just go ahead and we multiply it out, and we'll just go ahead and multiply it out, which are 500 times our 2, all divided by 80 times 6, which should give us right around 2.08, and that would be moles of our ammonium phosphate. All right, so let's look at dimensional analysis one more time. In this case, we're looking at this, we're going from grams to grams. So in this case, we see that anytime we see grams, we're going to need our molar mass, and we see that there's the molar mass, and there's our molar mass. So we have our nitroglycerin molar mass and our CO2 molar mass. That's what we have. Remember, we always have to use our mole ratio, okay, to convert from nitroglycerin to CO2. So we're going from grams to grams. Okay, rules still apply. The same that applies, that you need to have, anytime you see grams, you need the molar mass, and that's why we have the molar mass twice, because we're going from grams to grams. So let's look at an example problem and try to tackle this. It says cholesterol, which is C27H46O, can be metabolized into carbon dioxide and water in a process very similar to combustion. What is the volume of water produced by the metabolizing 5 grams of cholesterol if the density of water is 1 gram per milliliter? So looking at this is, what is the volume? Now it gave us the density, which we can figure that out. If 1 gram per milliliter, basically with water, what that means is that 1 gram is going to equal 1 milliliter. So we find the number of grams, we find our milliliters. So it's really only going from grams of cholesterol to grams of water. Okay, so anyway, we need a nicely balanced chemical equation. So it's a lot like combustion. So we'll start with our C27H46 and O. Now combustion, remember, it's just with oxygen gas, produces our CO2 plus our H2O. So let's go ahead from here and let's balance it on out. Okay, so we have our 27 carbon. We need 27 carbon, so we put a 27 right here in front of the CO2. We have 46 hydrogen. Okay, and we have water over here. It has a 2 right there. So 46 divided by 2 is going to give me right around 23. Okay, so we're looking at our oxygen, and what we see is that we have 3 oxygen. And over here, we have our 27 times 2 right here. That's going to give us 54, and then we have 23 oxygen, so 54 plus 23 is 77, which on our reactant side, we already have 1, so we just need 76 more. So what times 2 is 76? Well, that would be 38. So there's our nice and neat balanced chemical equation. Okay, so when we're looking at this, we just want to look at what we're dealing with. Okay, so we're starting with cholesterol, and we're trying to figure out grams of water. So the first thing that we always write down, that we're always going to use, always need, is our mole ratio. So let's go ahead and let's write that down. And we write that down, it's a 1 to 23 ratio. So 1 mole of our cholesterol, that's C27H46O, equals 23 moles of H2O. Now, since we're starting with grams and we're going to grams, we're going to need the molar mass of both of these guys. So we find the molar mass of both. Water, you should have memorized. 1 mole of water is right around 18.02, so we'll just say 18 grams of water. We use water a lot, that's one you might want to memorize. And then all we have to do for our cholesterol, 1 mole of our C27, so 27 carbons, 46 hydrogens, and an oxygen. That'll give us a molar mass right around 387 grams. Okay. And now that we have kind of our conversion factors set up, from here we just go ahead and we work out the problem. So we're starting with our 5 grams of cholesterol. So 5 grams of our C27H46O. Set it up. We'll probably use that much space. And we see we're starting with grams, so we got to go from grams to moles. Well, we use molar mass for that. So we'll go ahead and put, I don't want to take all of that. Go ahead and put that guy on the bottom. There's our conversion factor. Okay, that on the bottom. Put the other half of it on the top. We can see it there a little better in black. And then we keep going. We see that this unit will cancel, and now we need our mole ratio. So to convert from moles of our cholesterol to moles of water. So we take this guy right here, goes on the bottom, and the other part of the conversion factor, it equals, goes on the top. And then we keep going because we need grams of H2O. So match it up. We have to multiply. Oh, forgot our 1. Make it black so we can see it. And then all we have to do is multiply the top. So 5 times 23 times 18, all divided by our 387. And we should get an answer right around 5.35 grams of H2O. All right, let's move on to our next problem. It says that uranium hexafluoride reacts with pure sodium in a single replacement reaction. How many grams of pure uranium can be extracted from 2 kilograms of uranium hexafluoride? So a little bit of trick here. We see that we're starting with 2 kilograms, which we need to go ahead and convert that into grams. So that would just be our 2,000 grams of uranium hexafluoride. So we would have that. Okay. And when we're looking at this, if we have 2,000 grams, we're going to convert into how many grams of pure uranium. So when we're doing this, need a nice balanced chemical equation. So it's uranium hexafluoride. So when we're looking at this, uranium hexafluoride, so it's uranium, and then hexa is going to mean 6, so 6 fluorines, plus it's reacting with pure sodium to produce our it produces our pure uranium, so just uranium by itself, and it's a single replacement. So now sodium is now bonded to fluorine, so we have to crisscross there, which in A and F they're both plus and minus, so we crisscross the ones and it's just NaF. Okay, so from here we just go ahead and balance the chemical equation. So we need 6. We have our sodiums are balanced, uraniums are balanced, the fluorine's the only thing it's not. We have 6, we need 6, so we put a 6 right there. Okay, it changed our sodium, so we got to come back here and put a 6 right there. And now we have a nice, neat, balanced chemical equation. Now, in looking at the problem, it's saying that we're starting with 2,000 grams of uranium hexafluoride. So we're starting here, and it wants to figure out how many grams of uranium. So the mole ratio that we're going to have is just a 1-to-1 ratio. So 1 mole of uranium hexafluoride equals 1 mole of uranium. Okay, now since we're starting with grams and we're going 2 grams, we need the molar mass of each. So when we're dealing with this, we look at our molar mass of uranium hexafluoride. So 1 mole of uranium hexafluoride equals right around 352 grams of uranium hexafluoride. Okay, and then 1 mole of uranium equals right around 238 grams of uranium. Okay, now that we have our conversion factors, we know what we're starting with. We're starting with our 2,000 grams. We just go ahead and fill everything in. So there's our 2,000 grams. Start to fill everything in. So to go from grams of, and this is, or 2,000 grams of uranium hexafluoride. So to go from there to there, we need to go to moles. So that guy will go on the bottom. The other part will go on the top. Then we keep going, and we put our mole ratio, which there's a 1:1 ratio. And then we keep going, and then we put, to go to grams, we put moles on the bottom. Make it where you can see that. 1 mole of uranium equals the grams of uranium on top. And then all we do is multiply 2,000 times 1 times 238, all divided by our 352, which should give us an answer that's right around 1,352.3 grams of pure uranium.